Welcome back to our third lecture today. So it is called fluid dynamics. So let's get started. All right, so the forces acting on a fluid in motion includes all of these. So we have the gravity force, which is Fg, pressure force, which is Fp, viscous force, which is usually indicated by Fy, turbulent force, Ft, surface tension force, which is Fs, and compressibility force or elastic force, F of E. So these are all the forces that usually act on any fluid in motion. For Newton's law of motion for fluids, if the rate of change of momentum is equal to the force causing the motion, then we have the equation of motion as the following, which includes all of these forces added together, where m is the mass and a is the acceleration of the fluid. In most of the fluid problems, the external force and the static force may be neglected. Then the acceleration would include all of these forces without the external and the static force. This equation is referred to as Reynolds equation of motion. Then for laminar flows, the tension force is usually neglected, and then we have the Navier-Stokes equation, which is Fg plus Fp plus F of V. In case of added fluids, the F of V is 0, so we have only F of G plus F of P, pressure force, and gravitational force. So this is my equation of Euler's equation of motion. This is basically a very brief summary of their equations because they are derived, but this is like the main thing that you need to know after all the derivations. So we are interested in forces which cause a movement of the motion, like volume, pressure, resistance, and inertial forces. We have 3D problems and 1D problems. 3D problems, which consider general forces, field, and theoretical, they include Euler's equations for added fluid, Navier-Stokes equation, which is for real fluid and laminar flow, and Reynolds equation for real fluid, turbulent flow. Then we have 1D problems, which consider gravitation. They include two main equations, Bernoulli's equations and momentum theorem. All right? So, and we basically, when solving, we will focus on these two and mainly Bernoulli's equation because the 3D problems are not that easy to solve and they include a lot of numerical simulations. Okay, so now I'm going to restate about the four main equations that I've just mentioned. So the fundamentals of fluid flow, they include the conservation of mass, which basically expresses continuity equation. Then we have Euler's equation, Navier-Stokes equation, which expresses the conservation of momentum, and Bernoulli's equation, it expresses the conservation of energy. So to start with, we're going to be explaining continuity equation. I'm sure you've heard of it before or have been through it in your physics classes, but continuity equation, it describes the conservation of mass within a fluid flow. It states that the mass flow rate into a controlled volume must be equal to the mass flow rate out of that controlled volume. Assuming the steady state conditions, mathematically the continuity equation can be expressed as the following, which is density 1 times A1 times V1 is equal to density 2 A2 times V2, where density 1 and density 2 are densities of the fluid at two different points in the flow. A1 and A2 are the cross-sectional areas of the points, like for instance a tube, and V1, V2 are the velocities of the fluid at those points. The equation could be also written in terms of volume rate, which is Q is equal to A times V. So we can say that Q1 is equal to, okay, so the equation states the volume flow rate into a controlled volume is equal to the volume flow rate out of that controlled volume. So the continuity equation is applicable for steady, unsteady flows, and uniform, non-uniform flows, and compressible and also incompressible fluids. Okay? All right, now we're going to be speaking about Euler's equation of motion. So Euler's equation of motion, it's a fundamental equation in fluid dynamics that describes the motion of an inviscid fluid. It is derived from the application of Newton's second law to a fluid element in motion. I'm sure you all know Newton's second law already. Euler's equation states that the rate of change of momentum of a fluid element is equal to the sum of the external forces acting on it. This equation can also be expressed in component form for each direction, x, y, z, in Cartesian coordinates. So simply, that's how I remember the Euler's equation using this equation. Only pressure forces and the fluid weight, or in general, the body forces, are assumed to be acting on the mass of the fluid motion. Ma is equal to Fg plus F of P. Euler's equations are applicable to compressible and incompressible, non-viscous and steady or unsteady flow. So this is the equation of Euler's equation right here. Okay, moving on, we have the Navier-Stokes equation. The Navier-Stokes equation are a set of partial differential equations that describe the motion of viscous fluid substances. They are named after Claude Louis Navier and George Gabriel Stokes, who made significant contributions to fluid mechanics. The Navier-Stokes equations are fundamental in fluid dynamics and are used to model a wide range of fluid flow phenomena. It is a generalization of Euler's equation of motion for inviscid. The equation is equal to Fg plus Fp plus F of v. The rate of change of momentum of an element is equal to the sum of net momentum, flux in the element, and external forces. The general form of Navier-Stokes equation for an incompressible fluid in three-dimensional Cartesian coordinates is as following, as you can see right here, where v is the velocity vector of the fluid, t is basically the time, p is the pressure, ρ is the density as usual, and v is the kinematic viscosity. F represents the external body forces per unit mass acting on the fluid like gravity. This basically denotes the gradient operator, and this delta square is basically it expresses the Laplacian operator. Moving on, in addition to the conservation of momentum equation above, the Navier-Stokes equation are often coupled with a continuity equation which represents the conservation of mass, where the delta times v is a divergence of the velocity field, ensuring that the mass is conserved within the fluid. When shear forces are included along with Euler's equation, an extra force term is introduced, which is this part. So in vector notation, we can rewrite this equation in this way. And finally, this is the Navier-Stokes equation right up here at the bottom. And this is why I remember it by f of g plus f of p plus f of v. Right? F of p plus f of v plus f of g, which is similar to the previous equation I've shown you in the beginning for all of the derivations. Now we're going to be moving to Bernoulli's equation. So Bernoulli's equation is a fundamental principle in fluid dynamics that relates the pressure, velocity, and elevation of a point in steady, incompressible flow. It is derived from the conservation of energy for a fluid particle along a streamline. The equation is named after the Swiss mathematician Daniel Bernoulli. In an ideal fluid, when the flow is steady and continuous, the sum of pressure energy, kinetic energy, and potential energy is constant. So it is the sum of all of these energies, pressure energy, kinetic energy, and potential energy is constant. All right? The Bernoulli's equation, we often remember it with the law of conservation of energy. The application of this equation, it is mainly applied in incompressible fluid problems and also in areas involving energy. The application of Bernoulli's equation is used in measuring devices such as venturimeter, Piget tube, and orifice meter. Alright, so now we can do a classification of the flow problems while solving. Based on flow characteristics and degree of complexity, we can basically divide the flow into these laminar and turbulent, time-dependent, steady or unsteady nature of flow, which is parabolic or elliptic, dimensional of flow field, which is 1D, 2D, or 3D, Newtonian and non-Newtonian, single phase or multi-phase. Like I told you, 1D is basically like Bernoulli's, and momentum is basically like Navier-Stokes equation, and also Euler's equation, and Reynolds equation. Those are all 3D problems considering general forces, fields, and theoretical. So that's it. We're going to be now moving on to our following lecture, which we will be speaking in details about the flow in pipes. So we will cover in details Bernoulli's equation because this is the main equation that is used in hydromechanics for solving flow in pipes. And also we're going to be covering as well flow in open channels. So see you in the next lecture.